Okay, can you see clearly? So, in the last lecture, after main content was over, actually there was the failure of our encoder in this OBS system. So, the lecture content, the last part was lost, but I I don't think that is important to our watchers, YouTube watchers. So I think that it's okay, but I'm not quite sure, even in this case, whether our lecture can be recorded properly, entirely properly or not. So first of all, we have to be careful about that. And anyway, this is lecture 13. Before starting today's lecture, I would like to announce the lecture schedule. So change of lecture schedule. So in this semester, we had a plan to make lectures even in a week for midterm examination. So since we don't have any midterm examination in this course, I had a plan to make lectures in next week. So next week we have midterm examination for other courses, but so I just cancel my plan. Instead of that, so we will make two recorded video as the final two last videos. So simply speaking, you will have lecture 24 and lecture 25 as a form of a recorded video. So please watch in December, early December. You will have these two things, and it means that actually you don't have any lecture in next week. So what you have to do is not just to take a rest, but think about your final project. So you know, the most of your grade will be determined by this the quality of your final project presentation. And as I told you before, so before the end of our lecture, you must submit the recorded video to me as a final form of your project, and I will upload it to my YouTube channel. And also your grade will be made based on the quality of that project. So I think that it is now right time to think about your final project. When you visit my YouTube channels, then you can actually watch the previous videos submitted by our previous attendees. So please make a use of that videos, so you will have certain information out of those videos. Okay, so then during this pause for midterm examination, starting from not so let me just make it more clear. So we will have no lectures in this week, starting from 18th and November 1st for this range. So please upload your post. Please upload a post in our LMS system. In our LMS system, you also, as a student, you can upload a post, and your post must include the thing like the tentative title of your final presentation. So when you upload your plan, then I will just review it and will give you some comments on the plan, and If it is okay, then you can just go ahead. And if I think that maybe that is too ambitious, then I would like to just to make it more realistic and practical. And yes, so the kind of feedback will be given to you. So please don't miss this chance to make a certain discussion with me about your final project. Okay, so today, the last lecture before our midterm examination pause, and today's lecture will be devoted to the oxidation. However, my focus is not really on the oxidation model, but in the previous lecture, lecture 12, we have studied transient method. Do you remember? At the time, we have discussed about the difference between backward scheme and forward scheme. So, and I remember that actually our homework number 12 was devoted to how can you solve your problem when we have a certain non-linearity inside our system. At the time, the model I gave you was actually the rectifier. So you have a PN junction and other component. So the response of your system just follows a non-linear way. If your signal is positive, then that can turn on your PN junction, and if your input voltage is negative, then it cannot turn on your PN junction. That was studied in our homework number 12. Today, I would like to say about the difference between backward and forward method. Although I told you that in the case of a forward, it looks like a much simpler method. However, at the time I told you that that is related with unstable solution. So instability is involved. So today we will talk about that one with our oxidation model. Of course, oxidation itself is quite important. Actually, in the process, among many different processes, oxidation is the very first thing we have to study. So we will just quickly cover some contents in this oxidation. Okay. So oxidation simply means that the process to produce a thin layer of silicon dioxide on the surface of a vapor. So depending on its reactions, we can think about two different ways to make this silicon dioxide. Anyhow, we wanted to make a silicon dioxide, but point is, if we add H2O or O2, so then sometimes we can have a byproduct, and in some cases we don't. And people think that okay, this is although it's not really true, but this is water vapor, so it looks like a wet environment, and this is just oxygen gas, and it doesn't contain water vapor, so it's like a dry condition. So that's the reason why we call it as a wet and dry oxidation. Well, anyway, in both cases it would be very difficult for us to survive. So of course, and also although not shown here, this reaction does not actually happen if we just add water on top of this silicon. So think about this one. You have your silicon vapor, and just press a certain button in your water spray, then can we expect any kind of a formulation of H2O, silicon dioxide? Actually not. This reaction or these reactions can happen only when we have sufficiently high temperature. Otherwise, we don't have any meaningful growth of thin oxide. And there is one thing we have to keep in mind, especially in terms of in terms of numerical analysis. Here we have this one. Amorphous SiO2 is formed by this oxidation process. So compared with quartz, so silicon dioxide, crystalline version of silicon dioxide, amorphous silicon dioxide, which is made from this oxidation procedure, usually have slightly lower mass density per unit volume. Its mass is considerably lower than silicon dioxide. It's a crystalline version. What does it mean? So if we can just closely pack silicon atom and oxygen atom in an ordered way, so maybe this will be the maximum capacity we can have. However, amorphous silicon dioxide is not placed in an ordered way. We just put silicon and silicon oxygen atoms on a little bit unordered way, so there is no, how can I say, the most compactly packed way. So that's the reason why we have a relatively lower weight density or mass density. So that is makes some problems in our numerical simulation. So let's say think about this one. Here we have silicon substrate. Of course, this backside is not oxidized. Let's say, then let's say this top part. Then we just provide O2 or H2O to make our silicon dioxide, and let's say that some part of silicon, for example, let's say 10 nanometer, the top 10 nanometer of silicon was converted into silicon dioxide. Okay, so if we just think about from the viewpoint of numerical analysis, then maybe one way is, okay, now we have this part just suddenly converted into silicon dioxide. So that will be quite happy to us. But unfortunately, the situation is not that easy, because here we have different volumes here. So per unit volume we have different numbers, different molecules. So although we have just used 10 nanometer thick silicon, but together with added oxygen atoms, the final shape of our silicon dioxide layer is not like just 10 nanometer thick. It is just something more. So point is, it consumes just 10 nanometer thick silicon layer, and also it is expanded over this gas layer. So we have relatively thick. If this was, for example, it was 10, then maybe this is like about 20 something, 20 25 nanometer. That will be the thickness of our resultant silicon dioxide layer. So, well, experimentally it is obvious. However, point is, if you are doing a kind of numerical analysis, what you have to do is, well, previously in your system, so you say that this is the interface, and below it we have a silicon, and above it, so maybe you say that this is gas phase, so nothing in terms of solid state material. However, your final result after this process simulation should look like this. So 10 nanometer is consumed, So now your interface goes here, and you must introduce also another interface between your newly formed silicon dioxide layer and another gas phase. So also now think about this one. You have made 1 hour long oxidation procedure. Then how can you simulate this procedure? Okay, I start from t equal to 0. Then suddenly go to 1 hour later. T equal to 1 hour. Then wow, now I have the final result. Unfortunately, it is not possible. You feel that, maybe all of us feel that, if we wanted to simulate this 1 hour long behavior, then what we have to do is first think about the first 1 second, and think next 1 second, and another 1 second. So we must divide this entire process time into several pieces and think about what will happen to this system. So let's say that we have a very small amount of silicon part, which is now converted into silicon dioxide. In this case, how do we express this intermediate state? So maybe you can expect that now we must have the interface point here and another interface point here, and if time elapses, then this point will move into that part, and that will move into that part. So however, since this is just a 1D problem, so thinking the special way to treat this kind of behavior is not that difficult. But please think about 3-dimensional case. Now you have quite a complicated base structure, and now you wanted to make oxidation. Then what will happen to your surfaces? Maybe that would be quite difficult to think about this oxidation. Please don't be confused with this oxidation procedure and other deposition procedure. It means that you can see many different procedures. However, in the case of this oxidation means that a part of silicon area or region is now converted into something other. If you are considering other deposition procedure, it is nothing related with consuming our pre-existing silicon layer. On top of a silicon layer, a certain new material is just added. So it's so now think about this one. This is ground, and it snows. Then what will happen? After snow is over, then you will have a certain thickness of a snow layer. But it does not mean that our ground level is now converted into something other called as snow ground mixture. So in this case, still we have a clear cut between ground layer and snow layer. However, in the case of our oxidation, always boundary is moving. So this is typically called as moving boundary problem. So it is typically regarded as a very difficult problem for us, because every time when we have a new structure, then we introduce a new mesh to describe this slightly changed system. That is practical difficulty in our oxidation simulation. So Then, so this slide is just to summarize in reality, in actual fabrication, what are important fabrication parameters to determine the speed of oxidation. So think about our requirement. Do you need fast oxidation or slow oxidation? Well, some guys say that okay, fast is always good because we can finish our work quite early. However, in reality, it is not that easy. So, uh, one thing is sometimes we wanted to have high quality. Sometimes we wanted to have high speed, quality and speed. And maybe you may guess that they are not obtained simultaneously. If you make it quicker, then maybe its quality would not be high enough. Also, if you wanted to make a high quality silicon dioxide layer, then maybe it will take some time. Yes, that is just summarized here, and you can see that dry and wet has two different tendency for speed and quality. And now let's go to our well-known Deal-Grove model. Although this is nothing related with actually the simulation, it is just an analytic solution or analytic model, but this gives us quite a good initial point for our discussion. So we will, in this course, we will just consider this Deal-Grove model only. And in this case, they have introduced three different mechanisms. So now think about this one. Here we have silicon, and actually here we can find so many silicon atoms. Then how can we expect the expansion of a silicon dioxide layer? Here in this pre-existing oxide layer, already the silicons are oxidized, so silicon dioxide. If you wanted to make other silicon dioxide layer further, then actually these silicon atoms not yet oxidized should be oxidized. So that means that anyhow our silicon atoms and oxygen atoms should meet together. Then where can we find the silicon atoms? Yes, we have silicon atoms here. Then where can we find the oxygen atoms? Yes, we can find them in this gas phase. And yes, if they meet together, then at an elevated temperature, there will be certain reaction. However, they are physically or spatially separated by this oxygen layer. Oh, sorry, not oxygen, oxide layer. So what we can expect is here we have oxygen atom, and that is penetrated into this oxygen layer and eventually meet silicon atoms which are there. Then they just converted into silicon dioxide layer. This is the basic model of our Deal-Grove model. So therefore, I will just skip the detailed derivation procedure of this Deal-Grove model because I have done it already in our previous lecture. Please watch my 23. I have used the same lecture material at the time. Please watch for the derivation. So after some later, then we will have this equation. This is just ordinary differential equation for our XO. What is the XO? This is thickness of our oxide layer. And if it grows and if it increases, it means that we have done oxidation. So here we have one. So time derivative of this oxide layer thickness is once again a function of itself. So it means that if this is given as a constant, then we can expect linear growth of our oxide layer. However, since we have here itself in terms of this lower part of this fractional factor, so it means that if we have thick enough oxide layer, then what will happen? If this is high enough, large enough, then this one or this lower part will grow, and eventually we can expect that the time derivative of our oxide layer thickness will approach to 0. So this means that just a slowing down of our oxide layer growth. Okay. Of course, here we have some parameters, capital A and capital B. Please think about what are they, and they are sometimes measurable or can be modeled for your calculation or from your experiment. So this is the equation we will use for numerical analysis. Fortunately, it can be analytically solvable, and this is the solution you will have as a function of time t. You have analytic solution, so you can draw it. And here one thing important is tau. What is tau? This is another time constant, but this is related with initial oxide thickness. Well, so since we are assuming that there are 3 layers, gas phase and oxide and silicon, so at the beginning of our problem we have to understand the initial thickness of this oxide layer. But it is okay, because even in our pure silicon dioxide, pure silicon vapor, anyhow we have native oxide. So if you have a native oxide, then due to when it is exposed to the just normal air condition, then we have extremely thin silicon dioxide layer, just one layer. So yes, we have just a native oxide layer, just one layer. Of course, this tau is not actually always corresponding to the thickness of oxide layer. If we say so, then maybe this thickness would be just 0.7 nanometer or something. However, in reality, this tau means that sometimes it can be a much larger one or thicker one. So anyway, please understand this tau is regarded as an initial condition. So in this case, this is the real analytic solution, and of course we can think about 2 limiting cases. So means that here we have tau, and tau goes to infinity, or sometimes t plus tau can be regarded as infinitely large number, or sometimes this number is regarded as a small enough number. depending on these two cases, if we have quite a large one, then we can neglect other finite values, or in the case of a short oxidation, we can introduce such kind of a Taylor expansion. So square root can be well approximated as this one. So we can expect that at the beginning of our oxidation, so thickness is linearly growing as a function of time. However, later on, now oxide does not grow quite easily. Then, so when you just have a look at its growth, so it seems like it is saturated. So here I have prepared one parameters taken from a textbook. So A and B are given in these numbers, and also initial value is given here. Now you have all three numbers required to evaluate this analytic solution. So now you can draw simply. This time is your t value, and this thickness is given as xo, and you can see that as a time being, now your thickness is growing. So can you say what is its behavior? So simply speaking, yes, so it is linearly growing. However, if that is really linear, then you can see that maybe you will have this behavior. And now you can see that there is a certain degradation. The degradation is starting, and after several hours later, maybe if you draw the span of your time axis wider, then you can see that this is almost not exactly saturated, but its growth is quite much slower. So you can draw it. So now let's go to the numerical analysis. This is just an analytic solution, so this is perfectly good for testing our numerical approximations. So let me just do it together with you. Here we start from the equation obtained from Deal-Grove model. Once again, here we have unknown variable, and its growth is once again a function of itself. So now let's solve this equation numerically. So we have already studied there are two different schemes, backward and forward. I told you that actually in reality, in our computational microelectronics, except for some narrow field, niche field like a Monte Carlo method, usually we prefer to have a backward Euler. So let me just test it together with you. So now here we have a time derivative term. How can we treat it? So depending on backward or forward, we can define two different approximations. Here I just show for the Euler one. If we calculate the time derivative at t sub k instance, then if we follow for the Euler, then we need to get the future value. So in this case, not t sub k, but t sub k plus 1. We need value at this future time instance, and yes, this is for the Euler. If we follow backward Euler, can you write down here? So this is related with tk minus tk minus 1. So past time instance, and also values sampled at those time points. Yes, this would be the backward Euler. So let me just go to forward Euler and backward Euler. if we have to evaluate our equation at our time instance t sub k, then read this form. So the left hand side is related with our fourth Euler approximation for time derivative, and now we have this form. The right hand side is just instantaneous one. We just take the values at t sub k. Then please have a look at, so when you have this form, we will say that this is the present form and this is known. Also this is present value of our thickness, and we will assume this is known. And what is unknown to us is this guy. This future value is not known to us, so we can just say that simply tk plus 1 will be just starting from tk value plus this right hand side term of our equation multiplied by tk plus 1 minus tk. That will be the expression for our future value x sub o at t sub k plus 1. You are now just looking at this expression. So simply speaking, if you have a certain present value, and if you set the time difference between your tk point and tk plus 1 point, you can immediately calculate the next value, the future value of x sub o. So it is quite easy to do it, so you can immediately solve this problem. Okay, so are you with me? Then now let's go to the backward scheme. If we go to the backward scheme, nothing has changed except for this left hand side. Left hand side, previously we had positive 1 and k for our indices. However, now we have tk and tk minus 1. If we do the same math, then we have this form. So, but please have a look at this one more closely. Okay, just like fourth Euler, we can evaluate it, but it's not. So here we wanted to calculate the value at t sub k, but in the right hand side still we have the value at t sub k. Even though you know this value, the past value given to you, but you must do some simple math to get this present value. And unfortunately, this is not a linear procedure. Since here you have xo, and here once again you have xo, in order to solve this one, you must solve a nonlinear algebraic equation. So, of course, well, actually its solution procedure is not that difficult, and even you can find the analytic solution. But anyway, it is not a linear system. So linear or nonlinear gives you completely different scheme, because if you have a nonlinear linear equation, then this is just a kind of a one-shot solution. However, if this is not a non-linear, not a linear system and non-linear system, then unfortunately you have to repeat in reality this solution procedure called as Newton-Raphson method again and again, and it increases the number of solution procedure considerably. So that is one point. Anyway, for the same problem, we can think about two different approaches. So I would like to wrap up today's lecture with homework announcement. we have already shown an example. The example means that the one I have shown it here. Okay, so A, B, tau, all of these parameters are given. So what I want to ask you is just to solve the same problem with either or both of forward Euler scheme and backward Euler scheme. Then maybe you can find that if you have a sufficiently short time difference delta t, then you will find that both of your scheme work perfectly. So you will have almost invisible difference between your analytic solution and the analytic solution, numerical solution and analytic solution. But point is now, the point is please slightly increase your delta t and your delta t. Of course, all of us now understand if we increase this delta t, both of our forward Euler scheme and backward Euler scheme will give us a wrong result. So everybody understand. But point is, in the case of a backward Euler, we have a degradation of a solution quality. However, it still gives us stable behavior. However, if you go to this forward Euler, then you will see some failure, entire failure of your solution procedure. So please test that one, then you will now understand why we are using or why we are preparing to use backward Euler scheme over the forward Euler scheme. So simply speaking, if we can maintain this delta t over our given problem, not restricted to this Deal-Grove model or any kind of system, if we can keep this delta t small enough, then forward Euler can be a good solution or good approach. However, who decide then the smallness of delta t? Depending on the system, there is a certain factors to set the maximum value of delta t we can have. Sometimes this condition for delta t becomes too tough to be met by practical criterion. So that's the reason why we wanted to use a backward Euler. For example, in the case of semiconductor device, what is the small value of delta t? In this case, for example, it is a kind of picosecond. So if we just introduce picosecond steps for our semiconductor device simulation, then yes, this forward Euler scheme works perfectly. But you know, sometimes our quantities are required just at zero frequency. We wanted to sometimes have a DC solution, but we cannot wait such a long time with these picosecond steps. Then another question is, then who decided this picosecond time step? Why we cannot have, for example, nanosecond or microsecond difference delta t for our system? It is in the case of our device simulation, actually Poisson equation becomes the limiting factor for our simulation. It means that if we allow quite a long time steps like a nanosecond or microsecond, then our electrons just moves for nanosecond or microseconds without any adjustment of electric field. However, you know that electrons themselves generate the electric field. It means that here we have an electron. Previously, it generated certain electric field, and under given that electric field, we just anticipate that its movement. Now it is moved into that one. During its motion, for example, if it goes this position or that position, electric field will change. Now we have a different electric field distribution. However, in the case of this Ford Euler scheme, we just keep electric field at this initial state 1 microsecond ago. So therefore, their motion just based upon the previous one. So now what will happen? So after 1 microsecond has elapsed, then it will have a new position, but its position is nothing related with the realistic position. So let me just make a very crude analogy to you. Now think about a load around a clip. Here, say here we have a clip, and here we have car road, and there is a car. Car is moving. If we are simulating the motion of this car, what will happen? Yes, if we have sufficiently short time distance, then okay, after 1 second later, the car will be placed here. Then the driver will adjust its velocity. So not speed, but velocity, direction will be changed, and now it will move it this way. After also 1 second later, it will move here. I'm not quite sure 1 second is sufficiently short enough, but anyway, this driver will adjust his or her velocity accordingly to the change of the situation. But instead of that, let's assume that now our delta t is just 1 minute. Then what will happen? So starting from this position, we say that okay, its velocity is given here. Then after 1 minute later, it will be here. Then okay, so then now based upon the information here, let's go to the other one. So it means that the complete failure of our simulation method. So simply speaking, always our systems have a certain reaction to our solution. However, if we adopt this kind of a Ford scheme, then this Ford scheme does not consider the change made during our delta t time period. So that's the reason why we must become very conservative to set this delta t value. If we set this delta t value over certain range, then we will see the failure of a simulation. So unfortunately, in the case of a device simulation, usually this time scale is just a picosecond, and this is related with certain kind of redistribution of our electric field, and especially this time scale becomes shorter and shorter when we have, so this is important, when we have high doping density region. So simply speaking, when you have a look at the Monte Carlo papers out of your library, then you can always find that your Monte Carlo papers always assume quite low doping density even for your source and drain region. Its a typical value would be just 10 to the 18 per cubic centimeter, or 19 maybe. So almost no Monte Carlo paper can consider like 10 to the 21, something like that. It is not achievable because, simply speaking, if they have to consider such a high doping density, then they have to in or decrease delta value quite significantly, more than 10 times. So it means that you have to wait more than 10 times to get the solution. Typical time order for get certain Monte Carlo simulation solution is like days, sometimes weeks. However, can you wait? If you, let's say that you have waited up to now 1 week to get your solution, but in order to get the solution for better or higher doping density, now you have to wait for 10 weeks. Can you wait for 10 weeks or any kind of a 10 times longer time? So it would be extremely difficult to wait for such a long time. So that's the reason why we have to keep relatively low doping density. Of course, previously, anyhow, even though we can reduce that value, that doesn't make much difficulty, because at the time, when they actively use the Monte Carlo method, the channel resistance is much higher than this source and drain resistances. However, nowadays devices are really extremely scaled, and even source and drain resistances plays critical roles in our actual device performance. So it will be very difficult to consider 10 to the 18 or 10 to the 19 as source drain doping density. Okay, so today's lecture is quite short, but I would like to wrap up today's lecture. So let me just once again announce that next week we don't have any lectures. However, during that week, please post your plan for final presentation. Then I will give you my feedback to the final presentation. And instead of 2 missing lectures in the next week, I will provide lecture 24 and lecture 25 in early December in a form of recorded videos. Okay, so that was all for today's lesson. Then please use your next week, no lecture week, for catching our lecture progresses up to now. So we will make more advanced topics starting from the second next week. So please be prepared and please review and catch up. Okay, thank you for your attention.